Good morning and welcome to probably the most difficult video that we made so far. So this one is about Lewis structures. Lewis structures are a way to represent covalent compounds, and we talked about it a little bit. Lewis structures include these dots and lines, as you can see here. Now, this way of it that they explained in the book is pretty good. It's okay, but it's not advanced enough for what we want to do. It's kind of slow and it doesn't include some things. So please listen while I explain. So in a Lewis structure, you need to draw a bond between two elements in some compound. So let's say they give you a compound of H2, you want to draw it. Okay, H has one electron in the last energy level. Always draw an electron dot diagram first, and then the second one. And then when you connect them, make sure that they satisfy the stability rule. So hydrogen wants to have two electrons, so this is fine. Let's say they ask you to draw F2. How do you do this? First, check the periodic table, see where F is. F is here. It's got 7 electrons in the last energy level, so you draw it like this. These are dots, please remember. And then you draw it like this. This is a Lewis formula. So it includes the electrons which are included in the bond, and it includes all the electrons which are called free electron pairs. So they're not included in the bond, but they are in the last energy level. And again, first you put in all the electrons from each of these two F's. You draw 7, and then you draw a bond, and then you make sure that this one is happy. It's got 8 now, because now we count all these. So we count 1, 2, 3, 4, 5, 6, 7, 8, and on this side this one also's got 8, right? This method in the book is where you have two F's and then you put 14 electrons for both of them, and then you try to put them in a place. I find that inefficient. It's much more efficient to draw an atom and draw exactly what it has around it, because that's going to make it much more easier to attain deep understanding with more complex ions. Let's try something more that doesn't have the same atom, say HCl. So H has got 1 electron, Cl's got 7, and naturally what you want to do is this, and now this one is happy, it's got 2, it's got 8, this one is happy, it's got 2, but I mean, of course you don't draw this circle. This is a Lewis formula. It does get more complicated. For example, for let's say CH4. So C's got 4 electrons in the last energy level because it's here. I will not draw pairs here because I can estimate, I can predict that the electrons are going to go like this. And this is going to be a Lewis formula of CH4. There are no free electrons pairs because C also has only has 4 electrons. Now, please remember, first thing you do, you put all the electrons in the last energy level from every element in. The second thing you do is you make sure that each atom, after you connect them in the Lewis formula, achieves a stable state. However, there are a few shortcuts I like to use, and those are these. Mostly in the Lewis formulas you'll have these elements here, almost always. Because to make big complicated Lewis formulas that they might ask you, you almost always will need oxygen, nitrogen, carbon. So, and some of the halogens, so group 7 elements are called halogens. So please remember this. In the Lewis formulas, carbon always has 4 bonds. So those 4 bonds might be like this, they might be like this, they might be like this, or there might be like this. Now, it's impossible for carbon to have 4 bonds on the same side, so please forget that one. So why is this so? Because carbon is group 4, so it's going to have 4 bonds for sure, right? If it's going to be stable. There are some compounds where it doesn't, but mostly it does. Now let's talk about, say, nitrogen. Nitrogen is the next. Nitrogen's got 3 bonds. So it's got this electron pair and 3 bonds. Or it's got this electron pair and 2 bonds on one side and 1 bond on the other. Or it's got this electron pair. Oh, why did I write C? This electron pair and 3 bonds on the same side. So nitrogen easier. Then you've got oxygen, which got 6 electrons, which means it's got these 2 electron pairs always. So oxygen could be like this, or it can be like this. So it can have 1 double bond or 2 single bonds, right? And then you've got everything in group 7 is a halogen. So anything in group 7 is marked as X. So any X will have 3 free electron pairs and 1 bond. And then very often you'll have hydrogen, which will have 1 bond also. So by using this as a kind of a puzzle, you can puzzle together whatever they ask you. So they might ask you something crazy and long and difficult. You will still be able to puzzle this together. Let's see something which is maybe not so long but kind of looks complicated. Let's say we want CO2. So I know C's got 4 electrons, and I know it's going to have 4 bonds, right? And I've got 2 oxygens which have basically 2 electrons and 2 of these that are ready for bonds, right? And I've got another one here. So what's going to happen? I mean, this one's going to go here, this one's going to go here, this one's going to go here, and this one's going to go here. And if you want to, I want to draw this nicely, I will just go and do this. And now let's check if we've got enough electrons. You can also do what the book does and count the total electrons. So C's got 4 electrons, the last energy level, and 2 H's have 6 and 6 does 12. So that'll be 18. So you can just count if you actually have 18 here. And then that will be, oh sorry, 16, what am I talking about? So you can count if you have 16 exactly. So you know you're precise. But if you use my puzzle thing, you're not going to need to do that. So what I need to know, count now is, are they stable? Is every atom stable? So this one is stable because it's got 8, right? So 2, 2, 4, 6, 8, right? This one is stable, 2 and 2, 4, and 2, 6, and 2, 8, and this one also. So this is good. Okay, let's try another complicated one. I mean, let's do short but complicated ones right now. Let's try HCN. One of my most favorite ones. So let's try to do this with my method with just bonds, and then in the end we will count if we put in enough electrons. So hydrogen will do this, and carbon will do this, right? And nitrogen should do this, right? So this is pretty obvious. I'll just connect it like this, right? And then I'm going to draw this in a nicer way. C, N, and 2 electrons. And now I can count the electrons to be sure. So nitrogen should have 5, hydrogen has 1, that's 6, and carbon has 4, that's 10. Let's count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm good. Let's see if everything is stable. This one's got 2 electrons is stable. This one's got 8 electrons is stable. And this one's got 8 electrons. It's stable. So whatever they give you with these are called organic elements. Try to do it like this and you'll never make a mistake. However, it can get more difficult than this. How? Boron, for example, is famous for this because boron is group 3, but boron is almost always, not almost always, can have 3 bonds, or 1 double and 1 single. Almost always it will have 3 bonds like this. Why? Because boron is an exception. Boron doesn't want to have 8 electrons to be stable. Boron is stable with 6 electrons. Boron is stable with 6 electrons. Remember that because they give this as kind of a cheat. Aluminum doesn't do that. Not really, because aluminum doesn't really form covalent bonds that easily, but boron does. Then you've got also an example of sulfur. Let me show you. H2SO4. I will just do it quickly. So see quickly, and SO O O. So this is H2SO4, and you will see here, if you observe that everything here is okay, hydrogen is stable, oxygen is stable, but sulfur sulfur here, if you look at how many electrons in total it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons. So sulfur is also a weird element. Sometimes it's stable when it's got 10 electrons around it. Sometimes it's stable when it's got 12 electrons around it. So it can do weird things. The last thing, also very important, and I'm sorry this is a long video, but you do need to remember this. When they give you something with a minus, you have here an example, I think, of, Cn minus. The Lewis formula of Cn minus. You can do it the way they did it, which is they just took CNN and they added one more dot. So one more minus is dot. What I like to do here is, when I have a minus, I assume hydrogen was there and it left. So it's very easy for me to determine this. So I just, when they ask me to write Cn minus, Lewis formula, I will just assume that this used to be HCN, and then the hydrogen left, but it didn't take the electrons. So H plus left. So watch this. This is an excellent trick. It's going to serve you perfectly in organic chemistry. So as we did before, this is the formula of HCN. So what happens now? Since I need Cn minus, I don't need HCN. So I remove hydrogen, but hydrogen gets removed with these 2 electrons staying here. These 2 electrons, if they stay here, my cat is going to eat me. Go away. So we write them like this. Now, this is not a very stable element. And you can see, since now, carbon, technically speaking, has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right? And nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. It's all happy and nice, but where is the minus? You can see it says Cn minus here. Should I put the minus on this element, or should I put the minus on this element? That's determined by, if you want to know where is this minus exactly, on which element is, you take this bond, let me do this, and you divide it in half. So I want to see how many electrons are there for each of these elements. So look at this now. I've got 1, 2, 3, 4, 5 elements on the side of nitrogen. Nitrogen is group 5, so nitrogen having 5 electrons is fine. However, if I look at the carbon side, 1, 2, 3, 4, 5 electrons on the carbon side, but carbon needs to have only 4 electrons. So there's one more electron on the carbon side, so that means that this minus here is going to be on this side. So there's a minus on carbon because there are too many electrons around it. Sometimes they will also draw it just like this. They might draw just this and draw a minus here, which means that this whole thing is minus, but they might ask you specifically where the minus is, and this is how you determine this. This is not an ideal state because carbon does not want to have a minus. Carbon does not want to have a minus. Nitrogen should have a minus here because nitrogen is the more electronegative element. But carbon has to have a minus because there is no other way to draw this formula. If I reduce the number of double bonds. If I try to draw this like this, what N, and then I'm gonna have this. This doesn't work. Why it doesn't work? Because this one has 8, this one has 8, but oh, there's one more electron. Yeah, right. So this formula just won't work. So this is the only way to write it, to actually, for it to look properly. And again, it's much easier if you just assume there was an H plus there and then it's gone away. A similar situation you've got for this one, NH4 plus. I assume this is just NH3 with an H plus that came in. H plus can attach to any element that has a free electron pair. So if I draw this according to our rules, so NH3 should be this. So here nitrogen is happy, it's got 8 electrons, hydrogens have 2, they're happy. And then H plus comes in, but H plus comes in here without the electrons. So these 2 electrons here actually now become a bond to this H plus. And again, this is a very good practice for later. Now, where do you think a plus would go here? Well, again, you count only the electrons on the side of the bond, and you will see if you count the electrons on its side of the bond for nitrogen. Nitrogen here is 4, but nitrogen should have 5 electrons. So nitrogen actually is the holder of that plus. So NH4 plus actually looks exactly like this. You have other examples of Lewis formulas here, and I will give you some of these. I will ask you to do some of these just to practice. This is really important for what we're going to do later. Sorry for the long video, and good luck.